Hello again, and welcome back, or welcome in any case. This is Al, and this is lesson number 60, I believe. The last one was a two-parter, or three, quite long, and this one, if it's titled the way I'm intending to title it, is starts with a question. And I've been sitting here trying to come up with an answer, or several answers actually. So why do we care about the particular way in which this virtual function idea is implemented? You know, I mean, okay, so it works. That's one way it works. And what difference does it make how it works? I know it works, and I understand the concept, and everything's fine. And in a sense, that's true. It really, you don't need to know. But there are some advantages to knowing. Well, firstly, for me, I'm just curious. I like to know the answer to any question. I find it interesting, and to me, that's that's almost enough right there. But it is kind of interesting, though. Even though I kind of had an idea where it would go, that it seems like there's not that many different ways that you could solve that problem. So that's also interesting to know that there's some kind of general principle involved in it. And one of the things, though, even though I said that you should never depend on implementation details in your code, knowing an implementation can still help you write better code, right? Because it just it gives you a sort of a feeling for what's going on, and that might help in things like optimization or God knows. There's another one here that I'll get to. Another thing that we found out, anyway, comes from this number 3. Maybe I should have listed number 3 first. You remember that silly diversion? You probably don't remember the diversion because probably nobody watched it. But within the diversion, something came up. Because I was going through the memory, and I found out that these vtables are in the what's called the static, or the read-only static data segment. That's where these types of strings come from. Hello. Okay. This string, where it's stored in memory, is read-only. One. If I want to crash the system, that's enough. That right there is going to be an access value. Okay, I'll just pretend it's not constant. This is constant, not by virtue of keywords, but it's actually by the hardware of the machine. Watch what happens. See? Access violation. All I tried to do was assign, a value into this string, which is, I've just said, isn't constant, but I'm not allowed to do that. Okay, now those tables are in the read-only memory area, same as that string. Okay, now what does that tell you? It means that the entries in the tables can never be changed, right? So if you define a class like our base and derived thing, okay, they each have a vtable, and those vtables will never change. No. At least for this compiler, okay. That's a deep implementation detail. But you can still use that information to your advantage when you're building your program. You don't have to rely on it at execution, but you can use that knowledge while you're building your program. For instance, I know that if I'm using this compiler, that the vtable of an object is a unique identifier for its type. Okay. Now they have this runtime type information stuff. Here I'm talking about something else, but like this. Well, okay. Let me just finish this part. Knowing that allows you anyway to make a list of the tables you know, okay, and then you can associate a virtual vtable with a type, okay. And what I've said here is that means you can unvirtualize something. That is, you can find out what its type is just by finding out what virtual function table it points at, or is pointed to by it, or whatever the right wording is. And there sometimes that can be useful. An instance I was thinking of was these banks. You know, they have this software that has to run very, very efficiently and very quickly. And it turns out that some virtual function calls can cause what they call pipeline stalls, which is something to do with, again, with the hardware. When the processor is trying to decode the instructions, it tries to prefetch code that it thinks is coming up, right, and start decoding it before it gets time to actually execute it, and it does this in a kind of a parallel way. You know, you have these pipelines, but if there's a virtual function call that it doesn't know where it's going to branch to, and all virtual function calls are like call through pointer, so it has to make a guess as to what code is likely to be branched to. If you know the actual type, then you don't need to call through the virtual interface. Here's one thing I noticed. Okay, suppose I take my derived class and I do d dot one of the virtual functions. I renamed them mod because they're not constant anymore, so they modify something. Now, you look at this. That's a direct call, okay? Now, the CPU, when it sees this, it doesn't have to make a guess about what code is going to be executed following this line, and it can happily begin, decoding the instructions, even executing them in a virtual space of its own, and so on and so forth. As these modern processors can do a lot of things like that. Okay. Well, but typically, if I pass this to this here, to foo, right, which does the same thing, right, but it doesn't know the type. then when it gets here, it's not doing the same kind of call. Eventually it's doing a pointer call to whatever winds up in the DX register, and the processor doesn't know what's going to end up in there. It can only guess, and that's what they call branch prediction. It's the same problem that occurs with conditionals. When there's a switch or an if-else statement or whatever, the thing tries to predict. When there's no predicting involved, the code is extremely fast. This would typically, take like one clock cycle for the function. The other one maybe. If it's a miss, it might be thousands or millions of clock cycles lost. Because sometimes it just has to purge everything it's got in its pipeline. Now, the reason it knows which one to call here appears to be because, well, how can you go wrong? It says derived, and here's the D, right? There's no question about which version of the function I want to call. This is not a virtual function call. In fact, this is exactly what it says. This means D dot derived mod 0. Oops. Derived. Sorry. No. That simply says that, right? There's no ambiguity about it. It doesn't matter that this function is virtual. I'm not using the virtual mechanism here. I'm asking for it to call that function. That's what that says. Now, even if I make this a pointer, it's gonna figure it out. See? It's the same thing. It's going to the unknown address. But watch what happens when I do this. How did I do that before? I need a variable, I think. Yeah. Okay, here's a pointer to a derived, PD. Now, you'd think, right, that nothing's changed here. All I've done is assign this thing, right, into another variable. But in terms of what's going on, nothing's been added to this line except I moved this pointer to here. But that's not the way the compiler sees it. The compiler sees that as a virtual function call. Okay? It's not doing the direct call. It's calling the point. It's doing a call through pointer. Now I know that class is of type derived, and so I know that the mod 0 that it's going to go to is going to belong to that class. But the compiler doesn't, for some reason, because whenever it sees something coming from a memory location, TD is this expression, as we know, evaluates to the left-hand side, not the right. So it's invoking the code PD arrow mod 0. And PD is just a pointer to a derive. So it's not the same. Now you'd think it would be the same, but it's not. I could even assign it here. You know, you might think that it can figure it out by the declaration or something. And as you'll see, can't figure it out. But you know, right? You know what it is. So you can modify this. If you knew the type, and as I said, you know, if you can find out what Vtable is associated with, you can figure that out. You can turn this into a direct call. So what might have cost you a million clock cycles cost nothing. Going directly to that address. Okay, so that's one advantage to knowing about the implementation. Now, one thing that I always comes up for me, especially in that project I was working on. Well, maybe I could find it. I was just trying to find examples of things. That horrible project to do with the ID3 thing. I was this is like close to what I started out with, and I found these objects, okay, called ID3 reader, and everything's virtual. All the functions are virtual. And you might think, well, it's fine, okay, no problem, everything's virtual. But that means that, of course, now I don't know exactly, you know, what read cards does. I only know that my version does something, and another person's might make up another version, which might not be what I would expect. You know, if I'm using a reader object, and I'm expecting a certain type of behavior from it, and somebody overrides that behavior in a wrong way, that could be bad. Hopefully nobody would do that. The question is, how can you tell? And I found, I think this is the file. Yeah, here. Car reader, okay, so this is supposed to be a thing that reads all these things take, as in their constructors, take references to other reader type objects. Okay, it's a very confusing mess, but anyway, this thing, these are, somebody has labeled decorators. That is, they take that reader and they kind of spruce it up or something. They make it, add some decorum to it. Anyway, so this particular decorated reader is supposed to be a character by character reader. So that's the case for you. You need to read something one character at a time. And the example, for instance, they give here, it might be unsynced. Unsynced is a data format that has special characters in it, and you have to take special actions when you find them. So I'm looking, and I looked at the implementation of one of these things, and I put a comment. You can find it. Here's my comment. Okay, now see, this thing here is doing something bad. This one is also a car reader, right? And it's called a line feed reader. I don't know how they came up with these names, because what it does is it does not read line feeds. Okay, it ignores it. It skips past line feeds. See, found a character return line feed. Now D, I think. Oh God, I've forgotten already. D0A, and it's the opposite of a typewriter. Typewriter is line feed first. So D is carriage return. Okay. Carriage return, line feed. And if it sees a D and the next one's an A, it reads a extra character and returns just the D. Now, if you have a function that's called readCar, okay, and in the process of reading one character, it actually reads two, then it's lying, right? That's a lie. And the reason why that's a bad thing, okay, this is an example of not implementing your design. Another function might depend on the idea or the fact that if a thing reads one character, then it reads one character, and it might know and does know this class has maintains things like the number of characters and the current position and so on and so forth, and those things are not getting updated correctly, or they might get out of sync. Like suppose I want to seek 10 characters forward, but this thing ends up going 12 characters forward, and then I say, okay, now my current position must be last position plus 10, but that's not true because this one's lying. So you might want to prevent that kind of behavior. And the way to do that would be at least go and fix all these wrong bits of code. But how do you find out where all those wrong bits of code are? And one way to do that is to disallow further inheritance of this particular function, let's say. Now I actually did that to locate all these bad things going on, and this one too does the same thing. Unsynced thing, if it sees FF and the next one's a 0, then it skips one. So sometimes these things are skipping characters. So you can't write a generalized seek for that. Okay. Now what I ended up deleting all those. They were almost first on the chopping block. I just want to show you. I still never finished this because I'm doing these tutorials. What I did was I invented these reserved. I invented a macro called reserved implementation. Okay, so this here, this defines a function. This is the function name. It's the return type, and these are the arguments. So it's not written in the same way because it's a macro. It's not written in the same way as you would type it, but it resolves to that. Now, the way this reserved impl is implemented, okay, is actually by making the function virtual, making it overridable. Okay, can I get there? Gosh darn it, I don't want that. Stop. I just wanted F11. Here. Now, virtual, and then the function name and arguments, and then sealed. Now, sealed is something that happens to be something supported by the Microsoft compiler. Okay, other compilers don't have it necessarily, but this one does, and I can take advantage of that. This is number defined away if it's the wrong compiler version. Now, sealed means not overridable. Okay, so if you define a function through this mechanism, wherever it was, here, then it can't be overridden. If I just defined it as a regular function, not virtual at all, someone could still write a function with this name, right? But basically what I want is I want this to be completely not virtual, not overridable within the class or outside the class or anywhere. This is the only seek function that I want to exist. Then I can rely on it and trust it. Similarly with tell position and a bunch of others. These are all reserved, and what the person who is implementing this, a version of this class is responsible for doing is only pretty much one thing, okay? That's the function they've got to implement. And that's it. And maybe this one. Okay? And what that allows, now that I can trust all those functions to behave properly, is I can add all these much needed functions that I needed in order to clean this thing up and make it work properly, which is to be able to scan forward and find first and etc., just as if the thing were a string. Anyway, so that's an example of one thing you want. Oh, and about the performance thing, in debug mode, these are virtual, but if you go and build it in the release mode, they're not virtual. So then you get the next advantage of the thing that you release uses regular direct function calls, but no calls through pointers stuff. So it's another thing that you don't realize these things until you think about it a little bit. Now, knowing, for instance, the number of Vtables that you run into, okay, could, I'm pretty sure it wouldn't be hard to invent a kind of final. I don't know if you know Java programming, but in Java they have a thing called final, and that is a class with a final keyword, declared with a final keyword, is not, no functions can be overridden for that class. Now, if suddenly you found a new Vtable show up, then you could, maybe assert or something, or maybe you could use a template assertion or some other way to to fix and limit the amount of inheritance that you want for that particular class. So those are two things. And there's another thing that you can do that I just figured out. You see, and again, that actually goes back to the other project. I'll show you an example. This ID3 library, the fails project, has what they call a C wrapper part of it, or whatever. All of these functions, okay, are C functions. They're not C++. somebody who's writing a C program would use these functions, and everything that's returned is, if it's a pointer, it's a pointer to void. I'm going to find an example of something like a handle, or here. I'll find one eventually. Okay. Yeah, see, these all say H something, right? Handle to frame, handle to frame. There are other ones, other types of handle to field, right? Now this is taking one in. Yeah, this is, so this is, assume that the user has asked for one of these things and it's been allocated and handed over as a pointer to void. Now they're passing it back in to do something with it. Okay, they want to get the field or something. And here, they're trying to get the frame. I need to reframe, get field. What am I reframing? Yeah, okay, I'm getting a field. They have a handle to a field, and then, is that what I'm returning a handle to a field. Okay, I'm being given a handle to a frame. This thing has frames, and inside the frames are fields, and returning a handle to a field. Now, well, you can see it right here. This here assertion asserts that the pointer passed in is of the correct type, that it ought to be this type of object, and that's using just dynamic cast. Dynamic cast is a runtime type information type thing that tells you that can convert from a pointer to void into a dynamic, into a polymorphic type, and hopefully the one that you expect. If it's the wrong type, then the assertion goes off. And there's all these things all over the place. Assert dynamic type. Here is one, make sure that it's got to be a field if I'm going to compute the field size and blah blah blah. Okay, and different handles and different things. Now, okay, but that's something to do with RTTI, runtime type information. Now suppose you're doing that sort of thing with your I prepared this example. You're doing that with your library, your ID3 lib, and everything's going along great. Okay, here for instance, this is the analog to that field thing, and so I'm getting a pointer to something from the outside world, and I want to check to see if it's of my type derived. So I would say derived star PD equals dynamic cast to derived star of the thing I just got. Now this is called an upcast because I think it's called an upcast because I'm going from something a lower, something higher in the tree to something lower. Maybe it's called a downcast. In either case, now I want to know if it's of a specific thing that would derive from this type. Okay. And it turns out this one's going to succeed. And I've done that on purpose. And if that's true, then since it's of derived type, That means I can call my special override. You'll see that that should work as well. But I'm going to show you something that the dynamic casting and nothing else in the world I can think of will do for you. Now PD is not null, okay? So it's okay for me to call that function. It prints something out called virtual derived. Okay? Now, that, let's say it's the case of this, from that other thing, where I gave, I've been passing out derived stars to the outside world, and I get one back, and I'm making sure that I got the correct type back. Now, I only know about derived. Pretend. Let's pretend. It's certainly true. There's nothing else in this file. There's no further inheritance beyond derived. Now, what does that tell you? Given what we know about the implementation, you think that you should, press pause and think about that for a minute. What does that, from what we know, what is it that we don't know about this thing and that we could find out? Alright, I don't know if you thought about it, but if you haven't thought about it, what dynamic cast can't tell you, but that you know because of the implementation, is that it can't tell you that if this is something that inherited from derived. You know what I mean? Like, I only know about derived. So if I got something back that is a derived type, but I didn't make it, right? Then it's coming from the wrong, it's coming into the wrong place. Some mistake has been made. I might try to do something with this object which is incorrect. Maybe it's in the wrong list or something. You know what I'm saying? Now how can we check for that, given what we know? Well, we know that the virtual function table is a unique identifier for every type, correct? Okay. Now, what's the Vtable for derived? We should be able to answer this question immediately. We'll call it a T void. Vtable derived. What's that equal to? Well, I certainly can't tell if this, I can't extract it from this thing, right, because I'm not sure if this might be something further derived. But I could make a derived, D, take its address, right? Now that's a pointer to void star. If I interpret that as a pointer, a p void star, I know that everything at its address, the address of everything is a pointer to a Vtable. If I star this once again, that's now that is a pointer to a Vtable derived. Now, how about our friend here? Unknown. Well, we got a pointer. Again, there's p void. This one's already a pointer. We're going to star that. Alright. Now, let's run up to this point. Oops, if you can. Where am I? What's happening? Oh. Okay. this one, so p void star. Now it should be okay. Okay. F7. Locals. Okay. Vtable derived as before comes out to be this thing. The debugger has told us what it is, and that's the one we expect. Now let's see about our unknown. This is a Class E derivation of Vtable. See what I'm saying? These two virtual function tables are different. And yet this is a derived. A mistake has been made. Somebody has passed me a pointer that's of the correct type according to dynamic cast, but not of the kind of type that I've ever heard of. And so a mistake has been made, and now I've caught a mistake. And the reason I know it's a mistake is because I know how it's implemented. I know that nobody can overwrite my table. I know that if something is derived from me, it has to have its own table. So this is an assurance, a check, that it's of the right type. And this is a type I never heard of. Right? The compiler knows because it was compiled. So now I've alerted myself to a bug in my program, and I can go and fix it. So these things are helpful. Alright, well, that's probably too long. As usual, too long. I want to talk about destruction. That's the next important thing. You can probably guess that the destructor should in general be virtual, because like in this case, well, we don't know what type a thing is, especially this case where we have no idea what a Class E thing is, what a Class E derivation is. If the destructor is virtual, we can still safely delete objects of an unknown type. Okay, until next time.